The silicon controlled rectifier, or SCR, is a 3-terminal power control device that is a member of a group known as thyristors. Thyristors are 4-layer semiconductor devices that behave like a switch. That is, they are either conducting or non-conducting, on or off. Constructed from 4 layers of semiconductor material, P and PN, as shown in figure A, the SCR has 3 terminals, the anode A, the cathode K, and the gate G, as shown in the schematic figure B. The SCR is usually connected in series with the load as shown. Notice, the circuit is similar to the transistor or FET power driving circuit. In this case, the load current enters the anode and leaves through the cathode. The gate is used to switch the SCR from its non-conduction state off to its conduction state on. Unfortunately, the gate cannot be used to turn the SCR off, as will be discussed later in this section. Also, current can travel in only one direction through the SCR, as it does in a diode. The best way to explain the operation of the SCR is with the characteristic curve. Take time to consider this graph. First, recognize that voltage across the SCR is on the horizontal axis and the current through the SCR is on the vertical axis. The left side of the graph corresponds to the SCR being reverse biased, which explains why there is no current flowing, until reverse breakdown occurs at some high negative voltage. The interesting action takes place on the right half of the graph, where the solid line indicates the action of the SCR when there is no gate voltage. As the voltage across the SCR gets more positive, the current is held off until the voltage reaches a value known as the forward breakdown voltage, at which point the SCR turns on and the current starts to flow, and the blocking voltage shrinks back. The SCR is now in the forward conduction region and is acting like a low resistance closed switch. If the current is now reduced back to the value known as the holding current, IH, the SCR will immediately switch back into its high resistance non-conducting state. We now turn our attention to how the gate voltage affects the operation of the SCR. When the gate voltage is VG1, the forward breakover voltage is significantly reduced. That is, the SCR will turn on at a lower anode cathode voltage, indicated by the dashed line. If the gate voltage is high enough, called VGT, the SCR starts conducting right away and requires almost no forward breakover voltage whatsoever. This is the turn-on mode most practical SCR circuits use. Once the SCR starts to conduct, the gate voltage can be removed and the SCR will remain in the conduction state. Therefore, in many SCR circuits, the gate signal is actually a short trigger pulse, just long enough to ensure that switching has occurred. Turning on the SCR with the gate is relatively easy, but turning it off is another matter. There is no way to command the SCR to turn off. The only way to turn it off is to reduce the load current below the holding current IH. For DC circuits, this can be done in a number of ways. The first method, illustrated in figure A, is to open the load circuit with some other device, such as a switch. The second method, called forced commutation, involves momentarily forcing the voltage across the SCR, VAK, to 0 or below, thereby stopping the current. One way to do this is illustrated in figure B, where a shorting transistor momentarily reroutes the current around the SCR. Another way is shown in figure C and uses a second SCR, SCR2, to turn off the main SCR1. The current works as follows. When the main SCR1 is on, the anode voltage is practically 0 volts. Therefore, the capacitor C can charge up through resistor R. To turn off the main SCR1, SCR2 is triggered into conduction, which pulls down the voltage at the positive plus end of C to 0 volts, temporarily causing the negative end of C to drop as well. The negative voltage on the anode of SCR1 turns it off. Finally, when the capacitor discharging current wanes, SCR2 turns off by itself. Turning off the SCR for AC circuits is not a problem, because it will naturally turn itself off every negative half cycle. Remember, the SCR can only conduct in one direction. So AC applications, the SCR must be triggered on once for each positive half cycle, and then it will turn itself off at the end of that positive half cycle. Because SCRs work so well with AC, they are often used as the rectifier in an AC to DC converter, for example, to control the speed of a DC motor. A simple SCR speed control circuit is shown in Figure A. As you can see, the gate voltage is supplied by the AC itself through potentiometer R and diode D. When the level of the gate voltage gets high enough, the SCR turns on and it stays on for the remainder of that positive half cycle. By increasing the resistance of R, the time at which the SCR fires can be delayed, thus causing a shorter conduction period. These power bursts are averaged out by the load, such as a motor, into an effective DC voltage. The circuit just described can only control the trigger time from 0 to 90 degrees of the sine wave. To delay the trigger point beyond 90 degrees, a capacitor can be added to the gate circuit as shown in Figure B. As the capacitor C charges up through R, V lags behind. Remember, this happens for each cycle. Using this circuit, known as the half-wave phase control circuit, the SCR firing can be delayed up to about 170 degrees, resulting in such a narrow on time that the DC equivalent is practically 0 volts. The AC to DC converter circuits described in the last slide are half-wave rectifiers, which means only half of the potential AC power is used. The SCR can be used in conjunction with full-wave rectifiers to make use of more of the AC power by giving 2 power pulses per cycle. Such a circuit is shown and is known as a full-wave phase control circuit. The waveform from the SCR current, IAK, depicts the situation where conduction starts at about 90 degrees. On real systems, voltage is easier to measure than current, so it's important to know what the voltage waveforms look like. Notice that during conduction, the SCR voltage VAK is practically 0, and when the SCR is off, it assumes the entire line voltage. Some other conditions, besides those already mentioned, could cause the SCR to turn on. If the voltage across the SCR, VAK, rises too quickly, the SCR may turn on, even if the voltage is below the forward break-over voltage. This is called the dV by dt effect. To eliminate this possibility, RC snubber circuits are connected across the SCR to prevent the voltage from rising too fast. After turning off, VAK and IH must be held low for a given period of time, or the SCR will turn on again. As the SCR temperature increases, the required breakover voltage decreases, thus possibly causing the SCR to turn on. A different type of SCR, known as a LASCR or LASCR, a light-activated SCR, uses light energy to trigger the conduction state. These devices have a little window that allows the light to hit the necessary PN junction. SCRs are available in a wide range of sizes, with current capacities from 0.5 to over 1000 amps. Specification sheets are available to aid in selecting the correct SCR for your application. An explanation of some of the parameters used are as follows. The VDRM is the peak forward blocking voltage, VRRM, the peak reverse blocking voltage, ITSM, the peak surge current, IGT, the gate trigger current in continuous DC, and VGT, the gate trigger voltage, continuous DC. Knowledge of your application will require knowledge of these parameters. We now move to TRIACS. The TRIAC is a 3-terminal device that is similar to the SCR, except that the TRIAC can conduct current in both directions. Its primary use is to control power to AC loads, such as turning AC motors on and off or varying the power to lighting and heating systems. As indicated on schematic symbol figure A, the 3 terminals are MT1 and MT2, those are the main terminals, and the gate, MT1 and MT2, are sometimes called anode 1 and anode 2. As the name suggests, the load current passes through the main terminals and the gate controls the flow. Figure B shows the equivalent circuit of the TRIAC, which consists of 2 back-to-back SCRs with a common gate. When MT2 is more positive, the current flows through SCR1. When MT1 is more positive, the current flows through SCR2. The operating characteristics of the TRIAC are best explained using the characteristic curve shown. Notice that the right half of the curve in quadrant 1 looks like that of the SCR curve. No current flows until either the breakover voltage is reached or the gate is triggered, indicated by the dashed line. The same pattern is repeated in quadrant 3 for voltage and current in the opposite direction. Also, like the SCR, once the TRIAC is triggered, it will remain on by itself until the load current drops below the holding current IH. A single cycle of AC has a positive and a negative half cycle. The TRIAC requires a trigger pulse at the gate for each half cycle and works best if the trigger is positive for the positive half cycle and negative for the negative half cycle, although in most cases the TRIAC will also trigger if the gate goes negative in the positive half cycle and if it goes positive in the negative half cycle. TRIACs are available in various packages, some of which can handle currents up to 50 amps, which is considerably less than the SCR. As we have seen in the preceding sections, phase control circuits using SCRs and TRIACs regulate power to the load by turning on for a portion of the cycle period, as shown. For each half cycle, the SCR or TRIAC delays for a period of time and then switches into conduction for the rest of the half cycle. Delay and conduction measurements are commonly expressed in units of time or as an angle. It is useful to be able to make conversions between these two measurements. In North America, AC power has a frequency of 60 Hz, therefore the time for each half cycle is 0.5 divided by 60 Hz, or 8,33 milliseconds. Therefore, delay time plus conduction time equals 8,33 milliseconds. When dealing with angles, recall that each half cycle is 180 degrees. Therefore, delay angle plus conduction angle is 180 degrees. Converting between time and angle measurements requires knowing the relationship between time and degrees. For a 60 Hz system, there are 8,33 milliseconds per half cycle of 180 degrees. Therefore, 8.33 divided by 180 equals 0,0463 milliseconds per degree, or 46.3 microseconds per degree. Looking at an example, for a 60 Hz system, a particular SCR delays 5 milliseconds before firing. Find the conduction time for the SCR and find the conduction angle for the SCR. The solution: to find the conduction time, use the equation delay time plus conduction time equals 8,33 milliseconds. Rearranging, we get conduction time of 8.33 milliseconds minus delay time, and solving yields conduction time as 8,33 minus 5, or 3,33 milliseconds. Therefore, the conduction time is 3,33 milliseconds. To find the conduction angle, use the relationship of conduction time and angle previously developed to convert conduction time to conduction angle. For 60 Hz systems, 46.3 microseconds equals 1 degree. Therefore, conversion factor is 1 degree per 46.3 microseconds. We can use this conversion factor to convert conduction time to conduction angle. Conduction angle equals 80 is 3.33 times 1 over 46.3 microseconds times 100 microseconds per millisecond, or 71.9 degrees. Therefore, the conducting angle is 71.9 degrees. Perhaps pause this and go through the maths, make sure you're happy with that.